Calculus Video 6, the alternative definition of the derivative. So we're going to look at what's called the alternative definition of the derivative. Same idea, same principle applies. We're still going to be using a series of secant lines approaching a tangent line to give the slope of the tangent line. Here's the main difference between the original definition of the derivative and the alternative definition. The alternative definition gives the slope of the tangent line, not the derivative function. So it'll give you a number, right? It'll give you the number 7, meaning like the slope of the tangent line is 7. Whereas if you remember last time when we had the original definition, it gave us a function. It gave us a function like -1 over x plus 3 squared or 2x squared or whatever it was. It gave us a function, and we took that function and plugged in the x value to find the slope at whatever x value you had, right? So the difference is this alternative definition will give you the slope at a particular point. The original definition will give you a function that gives you the slope of the tangent line at a particular point. Two just different ways to do kind of the same thing. We're going to start with a very similar picture to what we had before. We have a curve F. We have on that curve the point A. And what I want you to think of when you see this point A is that's a particular number, 7, 3, 5, whatever it is. And what we're asking for is, what is the slope of the tangent line there in orange at an A value, a value of 5, a value of 2, a value of 1, right? Whatever that A value is. What is that slope of the tangent line at that particular value? So that value has a point on the left there, and that point is given by A, f of A. Then we'll create the secant line by picking some other point x down the road a little bit. So instead of like a plus h, we're just going to call this point x, which gives that second point the value x f of x. And if you connect the dots there, you get a secant line that looks something like that, right? You can find the slope of that secant line by doing delta y over delta x. And in this case, delta y over delta x, the slope of the secant line, delta y over delta x is a little bit different than before. Before, remember we had f of x plus h minus f of x over x plus h minus x, which simplified into f of x plus h minus f of x over h. This time, look at the change in the y values. The second y value is f of x, the first y value is f of a. So the change in y is f of x minus f of a. And the change in x is the difference of the x values, x minus a. So it's a little bit different setup, even though the idea remains the same. And then, to get the slope of the tangent line, what we do is we limit it. And the limit here is not h goes to 0. There's not even an h involved. The way we limit it is by taking that x value and moving it closer to a. So x is now a little bit closer than what it was before. That would give us a point that maybe looks like it's here instead of the blue line. Now we get this red secant line. And that's going to get moving closer and closer. And the closer x gets to a, the more the secant line gets to be the tangent line. And so we have, for the slope of the tangent line, the limit as x approaches a. All right, the x value is getting closer and closer to the a value. X is approaching whatever number a we were talking about, of the slope of the secant line, which is f of x minus f of a over x minus a. All right, this is the alternative definition of a derivative. And just like last time, put a star by that. You should know that, but you should also know visually where that came from. All right, so let's try an example with our alternative definition of the derivative. Let's do f of x is equal to 2x squared minus 6x plus 1, and let's say the a value is 3. And again, when we use this alternative definition, the answer we're going to get is just going to be a number. And that number is going to tell us what the slope is when a is 3. Let's see, I haven't drawn that. 2x squared minus 6x plus 1. I know it's a parabola. I know it opens up. I don't know exactly what this thing looks like. Let's see, if I plug in 3, I get 9, 18, minus 18 plus 1 is 1. I get 0.31. I really don't know what this specifically looks like, whether it's here or there. Let me just I'll just give it a good estimate. And let's call this 0.31. We'll find out how close my drawing is here in just a minute. What I want is the slope of the tangent line. So, whoa, that's pretty bad. Let's try that again. There we go. What is the slope of this tangent line? To do so, we'll use the limit definition, the alternative limit definition of the derivative. I already have the f of x there, so let's just go the limit as x approaches a. Now, x approaches a, but my a value is 3, so I'm just going to go ahead and plug in 3 for a. It's f of x minus f of a over x minus a. And again, I can replace all those a's with 3's. So I could say this is the limit as x approaches 3. All right, let me actually... I'll go ahead and put this in as an a to kind of keep it consistent. As x approaches 3 of f of x minus f of 3 over x minus 3. Okay. Well, the one reason we like this is we're not doing the whole f of x plus h, plug in the x plus h, multiply it out, right? That we don't have to do that here, which makes us happy. We just have the limit as x goes to 3. Of f of x, which is 2x squared minus 6x plus 1, minus f of 3. Now, I already found f of 3. I kind of did it in my head a minute ago. But f of 3, I'm going to plug in 3 into my original function. That's 3 squared is 9, times 2 is 18, 6 times 3 is 18, 18 minus 18 plus 1 is 1. That's where I got this 3, 1, the y value of 1 there. F of 3 means what is the function value, or what is the y value at 3? That would be 1. Therefore, f of 3 is 1, so I'm subtracting 1 over x minus 3. Well, if I simplify this, I get the limit as x goes to 3. The 1's cancel out, plus 1 minus 1. And so I just have 2x squared minus 6x over x minus 3. Again, I can't cancel the x's here because that's x is adding and subtracting. In this case, subtracting 3. What I want to do is factor. Typically factor here. Sometimes multiply by conjugates, sometimes multiply by the common denominator, but for a polynomial here, factoring is typically the way to go. It's only 2 terms, so I'm just going to pull out the common term. They both have a 2, they both have an x. I'm going to pull out a 2x. So I get the limit as x goes to 3. Pull out the 2x. That leaves me with x minus 3. Oh, that's nice. Over x minus 3. So what would happen here, if I were to plug in 3 at this point, in the numerator I get 3 minus 3, that's 0. Denominator, 3 minus 3, that's 0. 0 over 0, that's indeterminate. We don't know what it is. But now that I see I have x minus 3 over x minus 3 that can be canceled, now I have the limit as x approaches 3 of 2x. Now, the answer is not 2x. We need to plug the 3 in where x is approaching 3. So as our x approaches 3, we get 2 times 3, that's 6. And that is the slope of the tangent line. Remember, slope often abbreviated or represented by m. We're saying that slope right there is 6. And we could once again find the equation of the tangent line doing the y minus y1 is equal to m times x minus x1. Our point here is 3, 1. Our slope is 6, so y minus 1 is equal to 6 times x minus 3. Y minus 1 is 6x minus 18. Add 1, y equals 6x minus 17, equation of the tangent line. Okay, let's see how we did here. Let me go over to Desmos real quick, just check it out. 2x squared minus 6x plus 1 looks like the curve there in black. My point 3, 1 is right there. 6x minus 17, y equals 6x minus 17 in green there is the tangent line. That looks really good. So I think we did everything correct. That would be an example of the alternative definition of the derivative, giving us the slope. Remember, it just gave us a number. It gave us the slope of the tangent line at a particular point. In this case, that point was the point 3, 1. The big negative on using this is you don't get a function as your answer. And a lot of times in math, physics, engineering, we need not just what is the slope of the tangent line, but we actually need that derivative function.